Ah, ça va? 水那个这个窗，一路是我一路是我一路是不是阿里是什么？是不是？其他什么？对啊。不是你提到我，是如果是不长那你可能就是说来那两个朋友起来，我经常说，我这个同学。我跟这个号码开始太非常了，他做那个动作需要他上有安哥来调整，对，早上这个他这个气温是手是特别大，特别注重那种力量，所以说我们在手里面去手。就那个，啊，就是有人。心中有吧？他做的什么？真的我明天把那小孩的话讲啥？我去穿那个，都可以哦。如果你一定要用那个就 proof base case，再 define x 那个所以那个怎么样 define 呢 ？x x 等于 x，那就完了。原来那是真的。我看过，我是问爸爸，就你运去付。我是怕考试我没有不好，你不用讲叫我想啊，可以样子拍，你看我想个 x 加 y 或者 y 减去 x 用。
马来西亚的他在泰国是要10点的时候，我觉得先去吃个小时。
我就盯着那个 YAPP，
哦，他是那个没需要那些被消失了。
你盯着那 edition， 我想马来西亚的 edition，
啊，
马来西亚的这样弄不到，
是，
对吗？我就直接拍。
后面是不是跟我身边的朋友都是笑了？
才稍微。
正在连接，正在连接，已解锁，请取出话筒。
Hello, testing. Okay, welcome back to the lectures. Today I think online attendance is not working, so we will resume manual attendance later. Yeah. What thing we should say? So first, okay. So let's talk about unless. So Chiang very nice found this example here. She won't go unless you go. If you do not go, she will not go either. But if you go, she will go. But then this violate what we talked yesterday because we don't allow the second last phrase to appear in our unless, right? So I go and consult ChatGPT, I mean like Gemini. So basically this is the daily speech problem. So it's a social contract that people would think that if I say what? If I say she won't go unless you go, it will implies that if you go, she will go. Okay. So this is like daily life problems. But in mathematics, we will stick with the first one. Okay, we will stick with what we had in our logic. But then you need to be careful sometimes. If you are speaking to a very logical person or you are speaking with some ordinary person, then you need to be aware of this. Okay, yeah. But in future, I don't know. Maybe I don't think we can really rule these things out because why language will appear is because of people's mindset. Okay, so language differ from races is also because of why this group of people would think of that. Okay, so why there's Chinese, why there's Korean, why there's English? Because these people think alike. Okay, so they devise a logical tools for them to use. So actually language, I'm not sure you learn how you learn language. Language is actually very logical one. I mean, logic in the sense of that race. Yeah. But then if you look across races, right, they should think similarly. Yeah. Maybe there's some minority problem, but then similar, they are similar. Like adjective could be right. Like hi, hello. Like we could I mean like I would say that the poem in Chinese is more elegant than the English poem, right? I would say that. Maybe in some sense. Yeah. Because there's a sound problem also, right? There's the phonemes, yeah, the sound, phonics and stuff. And then the adjective we use sometimes are more detailed than the English, I would say. Yeah, more detailed. Because English is actually a very modern language, if you know. It's evolved from like French, those European language. Okay, cool. So have we got this done? Okay. And then I want to fix a convention in this class. Although yesterday I say that we would like to include natural number inside, include 0 as our natural number, but then let's fix our convention now. So let's fix convention. This one is to match up with our assignment as well. Hopefully I can release it by this week so that you have more time to work on it. I think you have 2 weeks but to work on it. So natural numbers will define it from 1, 2, 3, and so on. Okay. But then those that include 0, I will put a subscript 0 under natural, this left end. Okay. Sorry, I have a 0, right? Let's put a 0 in here. Okay, to distinguish these two things. Is it okay? Yeah. For assignments, you are freely to use any reference, but then obviously you need to use the method in class because whatever we're gonna test you is like within the course scope. And then please write down the reference you use, like you use Gemini or you use this other test book. If you use my lecture note, no need to specify because you are meant to use my lecture note. Okay, but if you use other than those things that I mentioned, like textbook or other reference book, please mention it. Another rules for assignment is please don't copy, just copy. You can search, but write in your own words. You understand it, write in your own word. Then don't copy. Especially copy from friends. You can collab with your friends. So write down a collaboration statement that I work with Xi Yang, for example, right? For this question. But then don't copy exactly what people's right. Okay. So you can discuss idea and then write on your own. Use your own word to write it down. Is it clear? Okay. Yeah. So if you really want to score well, right, assignment is definitely something you have to do good because you can check answer, you can do research. You have to score 100. Final, I mean exam, then that's something that you cannot control. Okay. So give more rooms for mistakes. Okay. So if you really want to score well assignment, you need to do it properly. Don't do it last minute because I found a lot of my students like to do last minute. Okay, so if I give you 2 weeks, right, make sure you do it slowly, properly. Okay, don't wait until last minute. Okay, let's continue. Okay, let's continue. So, there are two things I want you to think about. Okay, I want you to think about the natural number that you know, and then the abstract natural number that we're gonna define. Okay, so the moral of the story is these two things will be the same in the end. Okay, so let's think about the natural number you know first. Okay, so what do you know about natural number? Can you tell me anything that you know about natural number? Anything. Okay, sure. Good, very good. So one of the observation you see is it is like a chain. Okay, this number is like a chain. 1, 2, 3, 4. It's a chain. What else you know about natural number? What can you do with natural number? Add, good, very good. Okay, so like 1 plus 2 is 3, right? Or 1 plus 1 is 1. And then you can multiply as well. Sure. You can count it. Okay, but then in this class we not caring about the cardinality yet. So I think you learned in discrete math, is it? Did you? Okay. Okay. Fine. Okay. So in this course we don't really care about cardinality yet. What? No, I don't care about that. uh, okay. So I think basically this is enough to talk about Peano axiom. Okay. Sure. So how about Peano axiom? Let me recall a bit. So please keep the 10 axiom in front of you, but I want to summarize it a bit so that I don't write everything out. So in Peano axiom, I want to highlight some property here. First of all, it is a non-empty set. So we start with something called one. So when we talk about piano, you really need to think about abstract way. And then turns out to be the same. Okay. So when I write one here, this one can be 2, can be 3, can be 0, can be anything. I just want it to be a non-empty thing. Okay, yeah. Not to be the usual end. Okay, so one is non-empty property. Okay, maybe I write down to emphasize to you this is about non-emptiness. Second is bunch of equality, right? So equivalence relation. I don't want to write it up. And then third is about the successor function. Okay, so this successor function basically is the thing that determine the whole natural number. So let me write down. When we talk about successor function, right? We want the image, okay, the image of this function should lies in n again. So this is the n from piano. If you like, I can put an n star here, but then unnecessary. Then this function is injective, right? We said that this function is injective. So n equals to m if and only if sm equals to sn. So one direction represent function, the other direction represent injective. You know which direction imply function? Left to right or right to left? Being a function. Left to right or right to left? Left to right. Okay, so you have the same thing. That thing should go to a unique thing. Okay, so it's a function. So right to left is being surjective. If you have the same image, you should come from the same thing. This is okay. The next one is you cannot just send your element back to the original one. Okay? Whatever you started with. Okay, you cannot send it back. And then next one is principle of okay, can we do that? Okay, so let's do that later. So let's add this in first. This Sn here is actually n plus 1. So this justify why this function called successor function. Okay, so because you send to the next successor. But even this, you should think of it like, I don't know what is plus 1. It's just plus something that I started with. Plus, you also don't know what is it. It's just addition to my n. Something I put beside n. You should abstract until this level. Okay, so n plus 1 is a new thing. It's a new thing. It's different from n. Okay. Next, I think the next very important part is this principle of mathematical induction. Okay, basically later we're going to use this a lot and a lot. So let's label this as axiom 9, okay, mathematical induction. So this is very similar to the one that we introduced, but slightly more general. So if K is a set such that you have 1 inside there, okay, so should I use red to push it? It's my red. Okay, so if I have 1 inside there, so my base case is inside there, my first object is inside there, and then for every n, if I happen to know that n is in there, I apply successor function, is still stay inside the set K. Okay, then I can get the whole n inside there. I can get the whole n in my K. Okay, if 1 is in K, so remember where do I get my 1 here? My 1 exists in natural number, right? Okay, let's say this 1 here appears in another set called K. And then happen to know that if for every n in n, all the other natural number also stay inside K and its successor stay inside K, then I will know that a K will contain the whole n. Okay. Does it make sense? Okay. Then the next few things are about the addition and multiplication of your successor function. So for addition part, we have for all nm, mn in n, n plus sm equals to Sn plus m. So once I have a description for S, right, plus 1. So you should think of this as a n plus m plus 1. And then this one is m plus n bracket plus 1. Have you guys start learning associativity in natural algebra? Start already? Not yet. Where did you guys learn until algebra? Group, right? You talk about before group, right? You learn about composition, group composition, composition in group, binary operation, right? So you learn about associative, right? Group has binary operation that's associative. Okay, so this is the associative property. N plus bracket n plus 1 equal to n plus m bracket. Should I write it down? Or should I write it down? Okay, let me write it down. So n plus m plus 1 equals to m plus 1. Okay, associative. Okay. Any from there? Okay. Hello, Parker. On the side of the corner. Can you follow? Yeah, okay. Try ask question. Try ask question. If otherwise, you'll get lost. Okay. And then the next one is about multiplicative. So multiplicative here, we will force that n times 1 is n, and then for all nm in n times xm equals to nm plus n. Okay, so yesterday we rewrite this down, right, using our definition of x. So n times m plus 1 is really n times m plus n. Okay. Open bracket. Okay, so these are the things that we want it to be true. So you should imagine that with these properties, you can do what you have done with natural number before. With this property, you should think that we are able to do everything you can do with natural number. Okay, let's prove it to you. So our first theorem is we can prove that if n is a natural number that's different from 1, then there will exist another m such that Sm equals to. Okay. So this says what? This says that this map is actually surjective. If you have any number that's different from 1, you have a pre-image. It's surjective. So you can build every natural number. Okay. But then I think we won't prove this yet. We will leave it to tutorial 2. Okay, we'll do it in tutorial 2. Left the proof until tutorial 2. Okay, so now you need to choose to believe first. We can build every natural number. Okay, you don't know how it looks like yet, but I can build anything inside there. Is it weird, this thinking? I don't know what is it, but I can build it. Is it weird? Not intuitive. I don't know what is it, but I can build it. Maybe this is a level that you need to go through when you go through abstract maths. Yeah. Okay. It's not as abstract. Later I will show you like what is 2, what is 3, what is 4 later on. Once we put more properties together. Okay. So now next property is as I promised, I should show you the general associativity in natural number. Okay, so meaning if x, y, z in n, why is it true that x plus y plus z equals to x plus y plus z? So in did Dooley introduce you natural integer as a group? Did he introduce natural integer as a group? What's the example of group you guys know? Integer mod n, but modding out by 0 is integer, right? Integer itself is a group, right? Is it a group? Integer. Group with what binary operation? Addition. Okay, so then you need to prove why is it associative. Dooley won't prove to you one. It just say it works. But in this class, we're going to prove to you why is it associative. Okay, how to prove it is associative. Okay, so the ground here is Peano axiom. We start with Peano axiom. But then in Peano axiom, just now we said that there's some associativity happening, right? Can you recognize what's the difference of that associativity and this associativity? Can I put it down here? So maybe I bring this line down. Can you see what's the difference? So I'm guiding you line by line how to construct proof, how to write a proper proof based on what you want to prove. Okay. So can you see based on what you have? Okay, so let me show you. In mathematics, okay, because you are a beginner, right? So you need to discern two things. Okay, two things in proof you need to get your mind very clear. Two things to write proof. You know what's that two things? First thing is what you want to show. Okay, sometimes I will write it as WTS. Second is what do you have? Okay, what's your assumption? Okay, so these two things you need to get very clear whenever you want to write down a proof. You need to make sure what you want to do and then what you have. Okay, you cannot say that I want to prove, but I don't know what to prove. I don't know what to use. Okay, so this what you have is either assumption, either definition, either axiom. Okay, so you need to get very clear that where's your ground. If you are in zoo, then you need to prove differently. If you are in farm, you deal with veg. It's the different thing. Okay. Okay. So definition, assumption, very important. So what's our axiom here? So there's a very related axiom here. You see what's the difference here? You see what's the difference here? The bracket is jumping, right? But then what's inside the bracket? What's inside the bracket? Can you see that one of them has one fix, the other one is random, but the other two is also random, right? So there's only one defer spot there. Okay, so this is the key point already. Okay, you know that this associativity is true for when z equals to 1. But then what do you want to show? You want to show for any random z. But then this random z is happening where? Happening in natural number. Okay, so this is where we're going to use mathematical induction, because mathematical induction will help you to prove every element in F. Okay, so we need to set up our proof towards that using mathematical induction. Is it clear? There. Okay. Well, so to use mathematical induction, go see what is the thing that you need here. If you want to like use this, okay, you want to use this, you want to make sure that you have n, right? So this n is happening in some set k. So in this case here, you need to have a set k. Set k such that one can work with this one is the no different one with the one in the axiom associativity axiom, you know. Okay. Then maybe the next step is to check this one, whether this can hold or not. So this is the job that you need to do. Okay. Roughly get the idea? Roughly get the idea? I'll try and write everything now. Okay, then you will see what's the whole picture. Okay, so now this is our plan. Okay, our plan. So let's work it out. Okay, so we need to find a k such that so we need to find this k such that this k can work for the n. Okay, then we are done. Okay, good. Okay, so let's see how it works. So let's prove. Well, let's define a subset of k so that we can use mathematical induction later. So k will be all the z in n such that for all x, y, n, x plus y plus z equals to x plus y. Basically, is our goal. This is actually our goal. Okay, so if we can prove that n is inside k, k is inside n, this means what? K is squeezed between n. So k is just n itself. So it will be true for all the natural number. So this is our goal. Why is it a subset? Because obviously we need to pick element from n to verify, right? So it's a subset first. But then with mathematical induction, n will be a subset of k. And then k is a subset of n. Then k is squeezed between n. Then k is just n. This idea, okay? K subset of n subset of k implies k equals to n. The definition of equality of set. Is it okay? Yeah, feel free to stop. You don't need to agree with me. Yeah. Okay. So let's put down my goal here. So I want to show k is equals to n using axiom 9. Okay, since k is in n by construction, So here I use constructional because I construct something new, okay? So we are left to show that. So okay, I think I should put full stop. So we are left to show that n is in K. But this one will be confirmed by this mathematical induction. N is in K. Everyone okay? Okay, so there are two things to check for mathematical induction, right? You need to make sure that one will satisfy the set property, and then second, if n is inside K, then you want to show that the n plus 1 is also satisfy the property. Okay, so there are two things to check here before we can apply this step. Okay, there are two things to check. So let's check these two things. Okay, first, maybe I put 1 here for you to recognize it. First, we show that 1 is in K. So let xy in n. Okay, so if you look at this sentence here, for all xy in n, so we want to check that this term all jumping around. Okay, so we want to check that whether this line, this equality here, makes sense or not. So then we want to verify okay, so maybe one step backward. So there are so many x, y, z here. Am I substituting x? Am I substituting y? Am I substituting z? Yes, you understand.
You can can choose one that you don't need to define like because x equal x by I can do. Y and z you need to define by the succession function. This is the answer. I know I do similar question. Is it correct?
Not really. We don't really care what is x and y. No, just anything inside there. We don't really care where it comes from. Doesn't matter. The point here is, if you deal with this random x and y, and then you add in another z, okay, it should satisfy the associativity property here. Make sense? Yeah. So I don't really care what is x and y. X can be equal to y. Doesn't matter. But the point here is, I want to deal with the third addition here. Yes, that's right. So you need to remember your goal first. Yeah, what's your goal? Okay, don't confuse with your goal. Okay, so first thing is we want to verify for z equals to 1. Okay, so we want to verify for the case of z equal to 1 first. Okay, so because we want to show that whether 1 is inside this set or not. So 1 is inside this set means what? They has to satisfy this equation here. Okay, so we want to verify that for all x, y in n. So you write down the set condition. Okay, so x plus y plus 1 equals to x plus y plus 1. But then plus 1 is the definition of what? The successor function. Okay, so if you rewrite in the successor function definition, right, what do you get? S plus sy, this is by definition. S plus fy equals to s of s plus y. Is this familiar or not? This is axiom. Yeah, axiom addition. In the notes, I think is axiom 10, 11, 11. Okay. So which is true by axiom 11. Okay. So we have the first thing already. So we need to do the second thing. Okay. So let's do the second thing. So next, we need to show that if z in K, then its successor lies in K. Okay, so we need to do this step by step. Okay, let's compute it. Because you want to show equality, right? You can start from left, start from right, doesn't matter one. Okay, I will start from the left. Right. Okay, so let me see. Right. Do you know what's our goal in this case here? What's our goal? From this sentence here, can you see where's our goal? Point to me, where's our goal? Goal is very important. Where's our goal? We want to show if Z in K, then SZ in K. So which one is our goal? Okay, I give you choice. I give you choice. Option 1 or 2. 2. Very good. 2 is your goal. 1 is your assumption. Okay, so 2 is your goal. So write down your goal. Write down your goal. What does it mean by SZ in what does it mean by SZ in K? Write it down. Okay. So K, how does K look like? So you need to look for K. K looks like this. Okay. So what do you want to show? You want to show that for every xy in N, x plus bracket y plus sz is equals to x plus y bracket plus xz, right? This is what you want to show. Okay. So to show equality, right, you can either work from left, blah, 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 to right, or right, blah, 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 to left. Doesn't matter. Okay. So let's start from left. Okay. So consider x plus y plus xz. Okay. So what property can you use here? So you need to think of a way that you can transform your bracket to x plus y. But then you only have very few axioms to work with, right? Yeah. What's the addition axiom you can try and play around? So here is somewhere you can do experiment. Just work first, play around first. There's not much thing you can do. What's the addition relation with S? Can you tell me one of them? Which axiom is really one addition axiom? Again, axiom 11. Let's play around with it first. So x plus become what? 11, if you use 11. S of y plus z. Right? Okay, so maybe I can use 11 first. Can I do more from here? Or can I do more? Again, let's do it again, right? Because you have some natural number plus s of something. Okay, so let's do it again. Becomes what? X of x plus y plus z. Sorry, I think the other way around. Right? X plus y. Okay, by axiom 11. And then remember your goal. What's your goal? What's your goal? Your goal is to put bracket with x plus y. Bracket still not x plus y. Is there a way to move this bracket? How? Because z is in k. So what does k allow you to do? Allow you to write this triple addition using associativity. So this one is s plus y plus z becomes what? Go back to your z here. X plus y plus z become what? X, y plus z. You can use inductive hypothesis here. Become x plus y plus z. Why? Remember, what's your assumption? Your assumption here says what? Because z is in k. Because z is in k by assumption. Okay, so you can use your inductive hypothesis. Sometimes we call it inductive hypothesis. Okay. Does it make sense? Okay. Okay, so you cannot forget you cannot forget your assumption because sometimes you remember your goal, you forget your assumption. You remember your assumption, you forget your goal. So if you can try and write down a table, if you want to tabulate them, okay. Otherwise, you forgot what you have. Okay. So what's your assumption? Really useful. And then what do you do next? What do you think? Do you want the x outside there or not? You don't want the x outside there, right? So you can reverse your axiom 11. Okay, so you can apply axiom 11 again. What do you get? X plus y plus nz. Okay, so this is your goal. Done. Okay, by axiom 11. Make sense? If you notice, I'm being sneaky. There's one part I didn't show you before using axiom. You found where is it? To use axiom 11, what do you need? What's the property of 11, axiom 11? What? Nothing? No, just say it's okay. What? Nothing? Okay, so when you use this addition property, right? What does it say? N and M has to be in natural number. But then if you notice, when I use axiom 11, I kind of imply that when x is in n, y is in n, the addition of them is in n. Can I assume that? Can I assume that? Is it closed under addition? Need to be proven. Okay, so actually there's a lemma here. Okay, so there's a lemma that we need to prove here. So this lemma, so let me write down this lemma. So this lemma is for every x, y in n. Actually, you can prove that x plus y is in. Okay, you need to prove this. Okay. Well, I will leave it for you to prove it. I have notes inside. I have proof inside my notes. But given what you inspired by this proof here, can you like construct a K that works? Can you construct a K that make this works? Because not that you want to prove something that's true for ON, right? So this is where mathematical induction should come in. You want to prove it true for infinitely many things. In particular, natural numbers. Okay, so can you define a set K that works to help you to prove this? Inspired by the associativity proof. You want to try? Okay, obviously it's a subset of N, but then the condition is important here. Okay, how does it help you to prove x plus y is in N? You want to try? Try, just try only. Yeah, wrong also doesn't matter because you need to learn from mistake. Yeah. But did you notice that we didn't run away from the question of when we define K, it's almost like the property that we wanted to prove. So here is the same. What's the property you want to prove? X plus y is in N. So maybe you can try and put x plus y is in N. Let one of them running first for all x in N. Okay. Then can you imagine what's the base case here? Can you imagine what's the base case here? So the question is 1 in K or not? If 1 is in K, what do? You are asking what? You are asking that whether x for all x in N, whether x plus 1 is in N or not. Is it in N? Axiom. Which axiom? Which axiom tells you x plus 1 is in N? Axiom 6. Axiom 6. Axiom 6. Oh, okay. So this one is Sn. Okay, good. Axiom 6. Do you need axiom 10? Why I write 10? Oh, okay. Yeah, axiom 6 and 10 because axiom 10 tells you what is Sn. And then axiom 6 tells you Sn is in N. Oh, okay. Can you try and complete the proof? Okay, from here. I have a solution inside the note. So you try and complete and then try and check the solution. Okay. So far, so good. Question? Okay. Try and write down yourself. I have solution, you can compare. So basically, after that, then we are done here, basically. Okay, so basically we are done here, and then we can say that we conclude. Where do we conclude? We conclude SZ is in K. So principle of mathematical induction implies that our K will contain N. Any questions so far? Any question? Okay, so maybe the technicality here is to build the K that works. Okay, build the K that works. Okay, so this is the technicality here. Make sense? Making sense? Can follow? Okay. Good. So we are using so here we are using y plus z is in N, and then the other one we are using x plus y is in N. Okay. Right. There are more property actually. Okay, there are more property. Maybe distributivity. Okay, require proof as well. Distributivity, and then commutativity also require proof. Okay, but similar. Okay, so try and write down a sensible K and then proof using mathematical induction. Okay, then you will get all the property you like for your natural number already. Then it's like what Eric here says, a semi-group. Because there's no additive inverse here. No identity even, because I start with 1. Oh, is it? Okay. And then maybe one comment. I think yesterday Chia mentioned about 5 piano axioms, right? Why not use the least one? Is it? Did you mention this yesterday? Less piano axiom. Right. There's a version, if you look online, there's a version of piano axiom is 5 only. Oh, you don't ask that? Okay, never mind. I asked it. Okay, so there's a more simplified version, okay, of piano axiom. But then if you use that, you need to start your natural number with 0, because then from there it will imply that the successor function should look like n plus 1. Okay, but then in this case here, we have to define it to be n. Otherwise, unless you start with identity, or or unless you treat this as an additive identity, unless you treat this as 0, but then it will be a bit ugly. But doesn't matter if you are abstract. But don't be too abstract until like people cannot understand you. That's the problem. I mean, the purpose of abstractness is we want to be as general as possible. Okay, as general as possible. It's not like we want to detach from reality. That's not our point. Our point is to get even closer to reality, because the reality is too big. So we need to like include as many things into one word as possible. Can you imagine or not? Can you imagine? I think there's a joke. There's a joke. The joke is sounds like this. So let's say the Bible. Do you know Bible? Bible, right? Or any religion books. If the Bible is really trying to explain the whole world, the world is like infinite. Can these finite words enough to explain the whole world? There's something you can think about. The finite words can explain the whole world. I think I watched the videos. It says that a lot of logic problems come from information loss. For example, when you talk about Apple, 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 only 5 letters. 苹果 only 2 words. How do you know what this apple contains? This apple is like got color, got taste, got texture, everything. How can these 2 words encode everything inside it? There is an information loss when we speak about language. So that's why we need you to explain who write and Malay saying who write. And you need to argue. Okay, it's not just Yes, no, done, finished. No, I don't know what's your yes, I don't know what's your no. Okay, you need to explain. Okay, so this is where argument comes in. Okay, we still have a little bit more time. Okay, let's talk about something very not off the topic, but then just to relate you to back to your reality is so we have some number system here. Okay, so natural number is strictly a subset of Z, and then Z is a subset of rational number, and then slowly we build towards real numbers. Okay. So when we go from N to Z, what happens is we add in the additive inverse, since you have learned group theory, right? So sometimes we call it a group completion. We complete into a group. Okay? And then from Z to Q is also a group completion. We add in the inverses, inverses of multiplication.
Okay.
Yeah.
Q without zero. Okay.
Yeah, Q without zero, it is Q without zero is unique. Yeah. So there's some technicality you need to deal with, lah. Okay. Some technicality you need to deal with, but then yeah, moral is like that. Okay. Right. So here I list down some number system here as well, and then see what's the relation between them using language of groups. Once you learn more about groups, maybe you can appreciate this table more. Okay, so what is real number? Actually, basically, is rational plus irrational. Then from there, you can build complex number, because complex number is real plus imaginary part, right? Times real. And then I'm not sure you learned about quaternions or not. Then there's like three imaginary parts. And then next part is quaternion, where you have 7 imaginary parts. And then this table here will encode the relation. But then I left it for you to find out what's the relation. Wikipedia, if you're interested. Okay. It turns out that I think these are the only number system you can. They prove it that these are the only number systems you can. Associative. Okay. To be associative. Be associative. These are the only possibilities you can consider. They prove it. It's a very hard thing. But
Only this be associative.
yeah. So it's you need to find out. Yeah, there's a proof. It's kind of hard to mention. Yeah. It's a very interesting result.
Also associative.
Or
Or
maybe I need to be precise on what kind of number system, but then you can try and figure out the precise statements of that. You can try and figure out the precise statement. Yeah. Try and figure out like what do I mean? Yeah. I just want to make a comment, but then you try and verify it. Yeah, in what kind of a number system that I'm mentioning? Right. Okay, so have I settled problem of why is 1 plus 1 equals to 2? What do you think? After speaking of these, what is why 1 plus 1 equals to 2? After you learn about this successor thingy, and how they add, how they multiply. What's 1? What's 2? 2, you can just imagine it as a successor of 1. I mean, if you want to define 3 as a successor of 1, also can. Doesn't matter. It's just saying that 2 is coming after 1, and then 3 is coming after 2. That's it. Well, that's whatever you know about. Yeah, if you want to permute the symbol, also doesn't matter. No. I mean, like in different language, you also have different 1, 2, 3, right? Like in Malay, I'm not sure that China student learn or not in your MPU. 1, 2, 3, 4, 5, 6. Yeah. Okay. So these words doesn't matter actually. What matter is what come next. What come next? What come next after 1? What come next after 2? What come next after 3? What come next after 1? What come next after 1, 2, 3, 4? Okay. Yeah, this is what all it matters. Okay. So this is natural number. Okay, I think we have pretty much done with natural numbers. Later on, we will go into irrational and real numbers. Yeah, any question on Peano axiom? No? Okay. Question? Can be random question. Chiang, no question today. You're quite quiet though. Huh? Carry no quiet.
Just now I asked you a question here, like why is it?
Oh, the number system sound.
Like why is it? Yeah, these are the only number system that like.
Okay. Sure. But then this one is not under the syllabus. Oh, I mean like okay, you can try and make my statement more precise.
I don't know.
I don't know how.
I don't know what you want.
Oh, okay. Sure.
Real numbers.
Understand what you say. So maybe you can try and repeat my statement to whatever research engine, and then see how they interpret my sentence. You can try that. But then I wanted to ask you whether you have question within the syllabus stuff or not. Yeah. Do you have question like the technicality? Because these are the things you're gonna test in your exam of assignment or what, you know? Yeah. Is it clear? What to define there, and then what tools you can use? Is it clear? Like what axiom you can play around with. Okay. I think your friend, okay, before that. Actually, your friend like always, not your friend actually, in general, like math student will like have a mindset of I give you this question, you should answer this answer, right? There's a model answer, there's a fixed solution. Okay, but then what I want to instill you an idea is from my class, right? You should learn to read from question, understand what the question want, and then straight away write down the solution. It's not that I guess what's the solution is first. Okay? I have a solution. I just want to put it in. Not like that. Okay, is to understand what the question want. Only I answer to that question. If you don't know the question yet, please don't answer yet. Okay, write down what you have and then what you want, what you have, what you want, what you have, what you want. Repeat the step. What you have, what you want. Okay, these two things are very important. What you have and what you want. Okay, where did I write it? Okay, repeat this. Because usually people don't know what to do is because they don't know what they have. They don't know what they have. Okay, they are missing info, missing condition. Okay, so you need to check back again. What do you have? And then remember what you want. Because sometimes people walk. You want to go keep more, but then you went to McDonald's. Yeah, this is very common. Okay, so you need to remind yourself what you want and then what you have, what you want. Until you reach your goal. Okay. So let's take a break. Let's break until 12:03. Oh, not associative. Then what's the 像这些 system 是 categorized as 什么啊？忘记了。让我找一下那个 statement 是什么。
上面的时候你就失去了，然后你从头到尾听到整个是那个数学。
让我找一下我 precise statement 是什么。
还没什么 number 这个没有。要找出这三个路。
那么多什么？哦 ，OK， 因为有些系统会符合这些运算。Yeah.
Because actually Victor is a very important thing in the Asian study that try to explain the two-dimensional. So that they try to simulate that it's two-dimensional, but after many tries they find that it doesn't mean it's two-dimensional. And after that, it's four-dimensional create the polynomial to use the four dimensions to explain the three-dimensional one of last.
Okay, maybe I add on Qi Yang part. Actually, it's not all the associative algebra. It's the thing that is having identity, and then there's a cancellation you have here, and then a norm algebra. So this is the three things that we consider as the last number system as orthogonal. There's 16 dimension, I think they say, but then they won't have this three property like. So this is the norm division algebra. And then this three property are actually related to something in algebraic topology about sphere stuff. Yeah. If you are interested. 就是那个 S1, S3 跟 S7 的东西。Vector field 还是 vector field. I can't remember the precise statement, but then yeah, actually it's not about associative, it's about these three norm division. Oh, this one? Real numbers? Wait. Yeah. I mean, like, yeah. Oh, yeah, sure. Oh, yeah, sure. Oh, if you want to rule out the Z mod 2Z stuff. Yeah. Do we have that, huh? I never seen it before. Do we have that? No division. There is. It's a matrix ring. You like PhD a lot. It's a weird stuff. Okay. I mean, if you like it, it's okay lah. Sydney, there's a bunch of people like doing PhD stuff. Yeah, Sydney. Jody Williamson. Yeah, they work with PhD stuff.什么？Is 恒玉 here, no? 张恒玉. Okay. Dan Jun Han. Chong Yut. Okay. Liu Chung Xian. Kai Zhe. An Hui Jie. 34所。哦，他才有跟我讲 ，OK，是哪一位是安徽界？刚才坐哪里啊？坐你旁边哦，坐你这个位置。OK， 下次我再看一次，我忘记了。安俊伟叫了吗？刚才？安俊伟 OK。参子晴、苍文伟、秦航一、林一恒，OK。百兴燕，好像他有在红杰没有。
走过来的时候看到他，他现在没
有。冲千位没有在啊，但是没有在这个国家。Ravelli 也是没有这个，还没有退出来。 阿叔他有在吗？哦，他有在，你没有问他现在周末没有拿这个课，还是他退掉？哦，OK，
我们有的课哦，我们还没有上。
谁是他朋友？你们是他朋友吗？你也是？
然后他们有，
哦，
大概
啊，你跟他很熟？
好基哦。
你没有问他周末没有上呢？还是他拿其他课啊？
可能是拿其他课，可是他连那个 M 也没去上。
ME？
我就是我跟他选一样的。
哦，OK OK，
选 M 就还有点
危险呢。
有可能是这个星期还没有在，他出去玩了。
OK。Chu Yushen，OK，Helen Lee，厕所，OK，Ong Hong Jun，Paul Yong Sun，OK，修诗慧，天乐，OK，Lau Qi Yang，hey, where are you from? I mean, like, which part of Malaysia? Oh, Selangor. Oh, Lao also in Selangor. Oh, are you, okay. I mean, like, sure. Originally from Selangor. Your parents. No, right? Ah, I see. Okay. Make more sense. I think not many Lao here, I guess. And in this way of Lao, I think it's certain dialect, right? I mean, what is it? Yeah. Ah, Fuchao, right? Fuchao, right? Putian is Fuchao, right? Yeah. Putian is in Fuchao, right? Fuzhou. No, me? Putian, I know. I think the dialect is yeah. I mean the dialect is close to Lingpingjie. Yeah, because in Sarawak there's a lot of Lao one. Everyone is a Lao. Liu Chang, Yuan Hao Ran, Li Chenyu. Ah, you are Li Chenyu. Okay, so you just joined us today. Okay, I had you in the Moodle already. You in the Moodle? Yeah, you can check our course info and the details there. Okay, I'll try to work out a schedule for you. Which week you need to type your lecture notes. You want to start with week 1 or you want to start with week 2 or you want to like every week there's someone doing it? What do you think? Huh? Yeah. Huh? What do you think? Huh? You want to start with week 1 or you want to start with week 2 or you want to like do everything? Huh? Week 2? Because they're like, okay, because your number is very symmetric, it's like 13 of you times 2. Okay, so I was thinking wanted to do 13 week or we want to spread it out to 14 weeks. If 13 weeks, maybe I can prefer start with week 2 lah. Is it okay? Okay lah? Okay, sure. Okay. Then I will schedule your revision assignment. So we'll start with week 2. Maybe week 2 start with lecture 3 lah. So 3, 4, 5, 6, 7, 8, 9, 10 like that. Okay, although lecture 3 is like in week 1 lah, but then we'll start with lecture 3. Okay. Because lecture 1 and 2 is like your discrete math stuff, right? Yes. What do you mean?
I mean like the week, the midterm week.
Midterm week.
Like delay. Then the next. No. I just like avoid the midterm week. Like maybe
You mean the assignment? You mean you repeat the handing the assignment later? Is it? Yeah, sure. You mean delay the due date, huh? Assignment due date.
I mean like if you want
Yes.
then the maybe week 8 midterm
Mm.
you give then week 9 for people.
No, I can delay the due date. I can delay the due date. I can delay the due date. You still do the midterm weight, but then you can hand in later. Is it okay? Yeah. It's quite flexible lah. Quite flexible. Actually, I will give you time to like change up to like end of semester. It's just that we want to keep you up with revision, so we put a soft deadline in that sense. Soft 1 week deadline.
They can type all the lecture.
Can man? So good who? Wow, cool, very cool. Maybe you can let me know who are they. Never mind. Okay. You don't want to disclose. Okay, I will find out soon. Okay. Find out soon. Okay, so ready to start? All right. So next, we will address the question that why finding R is necessary. Back in the day of Pythagoras, right? They really just deal with rational number. So meaning those number that can be written as a ratio. Okay, they think that those are perfect numbers already. They can describe the world with rational already. Okay, they are content with that. But then until one day, the one person tell the Pythagoreans, not Pythagoras itself, it's the team of Pythagorean. It's like, you are my student, right? So it's like Seng team like that. Then you know what happened? So the person tell them, no, square root 2 is irrational. You know what happened to that guy? Got killed. Seriously, I got killed. I think throw into the sea, if not wrong. Is correct, feed the shark, okay. So be careful sometimes when you want to tell truth. No wonder you don't want to tell me truth just now. I won't kill them. Okay, so I don't know. Oh, be careful, be careful. I don't know. I'm not responsible for that. Okay, sure. So why finding R is necessary? So the first theorem we're going to see is why square root 2 is irrational. Okay, so irrational meaning you cannot write it as a rational part here. Ratio. Okay, so proof. This is a very standard proof by contradiction. So we suppose otherwise. Okay, so let's suppose that we can write it as ratio. See if we got any contradiction. Okay. So suppose the result is false. Okay. So by supposing result is false, we have something to start. We can work with something. Okay, so this condition here is we need to make sure that M and N is in Z, and then such that M and N have no common factor other than 1. So meaning I simplified the fraction already. Yeah, I simplified it. Okay, so from here, what can you do with it? What's the definition of square root 2? Definition of square root 2 that you need to know is perhaps square root 2 times square root 2 is 2. This is the thing that you need to know. So meaning it is a root to the polynomial of x squared minus 2. That is the root of x squared minus 2. The polynomial of x squared minus 2. Okay. So then how do you play around with this? Well, you can write it as you square both sides. Okay, so you get 2n squared equals to m squared. Up to this stage, okay or not? I square both sides. Because two sides is the same thing, right? So one side I times square root 2, the other side I times m over n, and then I move the n squared up. Okay. So this one I agree. Okay, so what does this say? How many of you take elementary number theory, guys? Elementary number theory. I think most of you do it. Good. Okay. So I just taught it last semester. Okay. So, well, so from here, what can you observe here? You write m squared as a multiple of 2, meaning what? Good. So 2 divide m squared. Okay. But 2 is a prime, huh? So if a prime divide m squared, this prime have to divide m itself. Okay, this is a proof in elementary number theory. Or actually, I list it down as a lemma. You can go back and join the lemma proof. But then we will use it now. So what does this mean? So it means that m actually is an even number. Let me be more rigorous, pedantic here. So I say this is a lemma. I need proof. I prove it in the notes. Okay. So and then what can we do next? We got a new description of m. Then we try and put it back. Put it back. So I substitute back my m. So it becomes what? Become 4k squared. Okay, become 4k squared. Then what is the new equation we can get here? N squared equals to 2k squared. But then, can you play the same game to n and 2 or not? Can you play the same game? N squared equals to 2, meaning what? 2 can divide n squared, and then 2 again divide n. So n is a even number. Oh, contradiction. Where's the contradiction? Sorry? Yes, the common factor become more than 1 already. Okay, 2 is a common factor also. Okay, both of them are even. I thought you already simplified. No, okay, turns out no. So okay, so similarly, we deduce that 2 divide n. So consequently, 2 is a common factor of m and n, contradicting the fact that maybe I write here lah, m over n is simplified. Okay, good so far. But then this is not the proof that I present in elementary number theory, because by the time when we learn prime number, we haven't learned divisibility yet. Okay, so what we do there is we use a well-ordering principle. So somehow we tell them well-ordering principle first, and then we go. Okay, so that's the another proof. There's some brief history I think I get from Wiki. Hopefully it's not wrong. So how they come up with this illogical AE rational thing? So well, really, this ratio comes from rational. Okay. Ratio comes from rational. And then the rational is the usual English rational that you know. Do you know what is English rational, by the way? Sensible, is it? Sensible. Yeah. Sensible. Okay.
So actually, there's someone saying that Yiddish actually is a wrong translation, but actually this is right because actually ratio is from rational box also.
Okay. So if they say Yu Li Su is wrong translation, what they want?
Try to here means
so we have to say Ke Bi Su.
yeah. Actually the
Sounds like a Pokemon name. Yeah. Okay, sure. Good, very good. Cool. Right. So far so good. Okay. So we're gonna build real numbers now. Okay, because there are some extra number than rational. We're gonna build real numbers. Okay. So actually there are three things we're gonna introduce building this real numbers. Is a very big construction here. Not really complex, but kind of a big construction. Well, we will build it using a three set of axioms. Okay, so first of all is the field axiom. Basically, this field axiom is like a group axiom, but there are two group inside there, group operation. There are plus and multiplication. And then why is it called field? Later on, when you learn ring, when you have a multiplicative inverse, it becomes a field. Okay, so basically, it's a ring. So what's a ring? Ring is a two. There's a two group structure inside there. So that's why you learn with group. So once you learn group, you learn ring. Okay. So field is an extension of ring, not extension, a special type. And then next is order axiom. Why order is important? Because you want to know which number is greater than which number. Okay, so order axiom. Finally, this is the part that define the uniqueness of real numbers. Okay, in this world, there's one isomorphism classes of real numbers. I mean, if you follow all these definition, there's only one type of real numbers. Okay, that you can write down. You can write down in different form, but they are the same thing. Okay, isomorphic construction, which we call the completeness axiom. Okay, so completeness axiom actually is the focus on this class. Okay, yeah. Something about upper bound. All right. So let me give you this table here. So a few axiom is this bunch of things. So how to read this thing? So well, there are two group structure, right? So one of them is addition, the other is multiplication. Okay. So for both this binary operation, okay, you learn in abstract algebra, it satisfies this property. And first of all, is closure. Okay, being a group, you have to be closed. Okay, so meaning if you do the operation, you still stay inside the set. Okay, you still stay inside the set. And then associativity, we see already, right, in natural number. Okay, so we want it to hold in a multiplicative, also multiplication. And then there's an identity here, okay, addition identity and a multiplicative identity. Okay, so we purposely write down the left and right here. Left-right inverse is very important here. Okay, you cannot just have identity on one side. Inverses as well. Okay, you have both sides, and then we will denote the additive inverse as minus a, and then the multiplicative inverse as a inverse, a to the power negative one. Okay, so this is how we think about negative number. You understand? Okay, I want you to switch your mindset once you learn abstract algebra or analysis. When you see negative number is the thing that add to the positive counterpart, you get identity. Okay, I want you to think about negative 2 like that. And negative 2 is something that you add to 2, you get 0. Okay, half, for example, half is the thing that you multiply to 2, you get the multiplicative identity. So you go back to your identity. Depend on what operation you do. Okay, this you should how to think about the inverse. Okay, I tell you how to think about half, right? How to think about 3/2? Based on my description. How to think about 3/2? What is 3/2? Huh? How do we define 3?
Inversal.
But there's a 3 there, right? Inverse should be like 1 over something.
Product of 3 and the inverse of 2.
Good. That's it. Yes. So 3/2 is just 3 times the inverse of 2. That's it. This is how you think about all the other rational numbers. Okay? Can or not? Okay. Okay. Commutativity, I think obvious. Okay, should be everyone happy about it. Distributivity is the one that combines these two, how you can multiply at the same time. Okay, then this pretty much determine how you can play around with the numbers. So if you have this property, R is a field. Okay, so on both sides actually is a ring, and then let's see. So this part here will disregard 0. We don't have 1/0. Sorry, 1/0 is undefined. There's a lot of reasons why we make it undefined. So this 2 row itself is a group, and then if you put these 2 together, is a ring, and then you add in this inverse part, it becomes a field. For now, if you don't understand, that's fine. But then in future, you understand. Okay. If you don't understand, then you need to look at this whole table at once. Okay, this is a field. Okay. So in this sense here, the integer is just the set of natural number plus their additive inverse. Okay, so you have 1, 2, 3, 4, 5, 6, right? And then you add in the additive inverse, identity is 0, and then you add in all the inverse is the negative part. So you make up the whole chain of inverses. I mean, Z. Yes? Yeah, you need to add 0. And did I not add 0? Wow. It's amazing.
So that's why
Okay.
because it will be simplified a lot of things.
Sure. Depends on how you set up. Yeah. So depend on how you see it. So I will add 0 again. And identity. Depend on how you see. You want to simplify things. Because sometimes we cannot oversimplify because we want to make things precise so that people will know what's really breaking down things so that people know what we really care. Yeah. Yeah, you need to give and take sometimes. Yeah, you need to give and take. Okay, so what I want to try to share here is we know 1, 2, 3 already, and then we will add in 0, and then we will add in the negative part like that. Okay, to build the whole integer. Make sense so far? Okay, we start with natural number, and then we put in 0, and then we put in the negative. And then the rational, what is rational? We have the integer, okay, and then we can multiply whatever you do, and then with their multiplicative inverse, okay. For maybe need to be precise a bit. For z is not in 0. Okay, but then in this case, you might think that I thought multiplicative inverse for z not in 0 is just 1 over n. Then how do I get like m over n? How do I get m over n? Correct or not? If I just take z, not 0, the inverse is just 1 over n, right? 1 over 500 million, 1 over 10,000. But then how to get like 3 over 2, 5 over 3, m over n in general? How do I get that?
M equals 0 and 0.
I
don't know.
Doesn't matter about 0 anymore, right? But just now, remember how we define 3 over 2? You told me how to define, right? 3 times the multiplicative inverse, right? So this is what we meant by multiplicative closure. Okay, so we take these number and then we multiply together. These are still inside multiplicative closure. We consider their product. Okay, product with m and 1 over n. So this is how we define m over n. So let me write down here. So m over n should be defined as m times 1 over n, like that. Or if I use the notation I used later just now is m times n inverse. Okay, make sense? Okay, so this is what this multiplicative closure means. Okay, I multiply them, I have to let them stay inside my cube. Close it. Okay, so in this case, I can get all the m over n already. Okay, so this term is very important, multiplicative closure. Right, so this is how we say that their product is also in there. Okay, so some very basic axiom, you will see like your high school teacher tell you, 减乘减是加，减减加加减减，减加减加加加。So you have to prove it. Okay, you have to prove it from the axiom, few axiom. Yeah. So y minus 1 times a is minus a. You see, from the description we learned just now, minus a is what? It's something that add to 1 becomes 0. But then y, when you multiply to a, become an inverse already. Require proof. Okay, y minus 1 times a is minus a. Okay, and then this one is just minus jumping around, right? Which one is not intuitive? Do you think which one is not intuitive? We can discuss a bit. Even this, a times 0 is 0, have to prove. Usually you will think that everything times 0 is 0, right? But this require proof. Yeah. Yeah. And then why this is equivalent as making the denominator the same. Maybe we can pick top 3 most interest one we can prove together. Top 3. The other you can see the notes. Top 3. Maybe one from this side. Which one you're interested in? Top 3. Right? Which one you're interested? You. Two, you two. Okay, two. Okay, let's block two first. Okay, how about middle one? Middle. Got choice. Any choice? Middle. Pick one. 选一个。来 at the back， 哪一个有兴趣？没有兴趣就糟糕了，不应该在这个课出现。选一个。You want it? Okay. One more. 谁？那个叫什么名啊？那个后面那个。洪俊哈。OK， 来，洪俊你选一个。你选，你自己选。第九个 ，OK good， 第九个，第九个好像有点麻烦，不知道麻不麻烦，but then OK never mind。OK let's do 289 OK good， so let's do it 。每一个回家记住。I mean I prove it in the notes already, just that we want to discuss together. Yeah， 每个 you should try you should try yourself actually, you should try yourself. Okay, so what do you want to show here? A dot 0 equals to 0, right? So as like what I said just now, you can work from left, work from right, no matter how you work. But then I will choose from left. Okay, so how can you play with 0? What's the property of 0? Then you need to know what you have. What is 0? Anything plus 0, you get back to yourself. So, well, can I create a 0 or not? Okay, because it's 0 is a additive identity, right? Okay. Anything add to 0 is 0 itself. I mean the element itself. What else? What's next? What next? So there's less thing you can work with, right? So you need to kind of create more things first. Is there a possibility to create more things? How do you get 0 actually? One way is 0 plus 0, but then not very useful here. But you need to, okay, maybe the idea here is you need a right-hand side is 0, right-hand side is 0. So you need to think of how to get rid of the A0. You need to get something out to remove it. Right? Okay, can you get something similar to A times 0? Any idea? Left bracket. You said left bracket. Okay, so maybe you can create something like A times 0 plus its inverse. Can I do that? Right? Can I do that? Sure. Okay. But then how this helps? How this helps? Well, so maybe I write down this. Why can I do this? Because minus A times 0 is the additive inverse of A times 0. Okay. But then did you see that I can combine things now? Can I combine things? Using associativity, right? So I can see that there are two terms of A times 0. What can I do next? 2 times A times 0. Then non-stop already. Okay, yeah, good. Very good. Distribute. How do I distribute? I can pick up. Distribute is like factoring out, right? Factors out. Okay, so I can factors out A. Okay, become 0. A times 0 plus 0. But what is 0 plus 0? Is 0. Okay, so then I reduce one of the A times 0 to A0. Then what do you see? You really see that A times 0 cancelling out with the additive inverse. So you get 0. Cool. Okay. Yeah. So, okay. In your assignment, I really pedantic about this. Every single equal sign, you have to put reason. Okay. Just now I speak in words, but then try and fill it in. Okay. Every single line, you need to put reason. Okay. Since what? Due to what axiom? Why you can do that? If not, proof as a lemma. Okay. Every single line, you must put. Okay. Otherwise, I definitely will take off marks. Yes.
can we put existence of
Hmm.
like for example, A times 0 exists, like we're doing the term.
What do you mean A times 0 exists?
You have to assume that A times 0 exists, right? Otherwise,
Why don't exist? Because A is in R, 0 is in R, and then R is closed under multiplication. So it exists.
so yeah, you can see this.
This also, if you want to write this, also can. It's just that if I catch that the most important point you didn't write out, I will take marks. If I didn't catch it, then maybe you are safe to go. But if once I catch it, then you have no chance. For like really pedantic one is like what you say. What you say have to be true. Okay, you can write it out. I don't care. I can read it, make sense, that's fine. Just don't write rubbish to me, that's okay. That's okay. You can I mean like I have students like writing like few pages, but sometimes it's unnecessary. Sometimes we kind of know that it works, but then like what you say, like really 100% pedantic, you need to write it down. But then that won't be my marking scheme. That's what I wanted to say. But the most important, these the usual. Do you agree that these are the usual thing you have to really write down at least? Yeah. Obviously, your question makes sense. Makes sense when whether my question makes sense or not. Even correct or not? Yes, true. You are very true. Yeah. Okay. Good. I agree on that. Okay. So what's next? 8, right? What's 8? 8. 8 is minus A times minus B equals to AB. Yeah, so this question is very interesting, right? Why you multiply two inverses together, then suddenly becomes something new, AB. Yeah, this question is actually very interesting. Okay, so how should we do that? Like what I say, you want to work from left, work from the right, doesn't matter as long as you meet another guy in the end. Okay, how can you play with? So there is a reason why we list the axiom in this order is particularly because we are allowed to use the previous line. Okay, we are allowed to use the previous property. So it listed as number 8, right? So you should be able to use whatever come before. You understand? So there is a reason why we listed down as sequence, because this thing can be proved in sequence. Okay, so we can use whatever before 7, before 8. Okay, so what I'm going to use is actually number 5. I'm going to pull the minus out. Okay, I use number 5 to pull this minus out. Okay. Then you might want to ask why 5 works. Okay, you can try and prove it yourself. Okay, so let's try use number 5. Okay, let's do number 5. So this is one to show. So let's consider the left-hand side. So let's pull the minus 1 out first. Okay, so can you imagine what can I do next once I got this? What can I do next?
Associativity.
Yeah.
You can put negative 1 percentage, but then see what it becomes.
Yes, so use not just associative, right? Because negative 1 is not side by side yet. Yeah, so you need commutativity. Yes, so you need a bunch of associativity then plus commutativity. So let's see why associativity is necessary here. So if I associate, then I can pull the minus 1 out first, and then I associate A with minus 1 times B. Like this. Okay. And then what can I do next? I need to move my minus 1, right? Can I move minus 1 across yet? Can I move minus 1 across yet? No. Okay, because I need to make this bracket around A and minus 1 first, only I can compute. Okay, so meaning what? I need to do associate again. I need to associate again. So associate here meaning associate your bracket. Okay, so you move around your bracket. Right, and then you do commutativity there because they are in the same bracket already. And then associate again, right? Because I want to make the minus 1 in the same bracket. So I associate back. Let me see. Is this the right associativity? Okay, maybe like this first, the big one first. Okay, and then I associate the small one, right? Because it's not in the same bracket yet. See? Same bracket, so I associate the inner bracket. Okay, now then the two minus 1 will stay side by side already. And then do we know minus 1 times minus 1 is 1? Seems like we not yet know. Let me see. Is it one of the we not yet know minus 1? What is minus 1 times minus 1? Okay, so how to settle this? Yeah. 第三个 not really, right? This is minus 1 equals to 1. 好，我们有 minus 1. 要很靠近了，很靠近了，很靠近了。Yeah. That's right. Okay, so that's right. So we're gonna use number 5. Number 5. Let me see. Is that right? Okay, good. 对，没有错。Now we have to use 5 and 3. So if we use 5, okay, maybe let me copy them lah. Okay, otherwise I can't remember. You also can't remember. Let me copy them. Copy. Paste. Okay, where's my paste? Okay, so let's put it here side by side so that we can refer. Okay, so we're gonna use 5 first, huh? Okay, so we're gonna make it become minus of minus 1. A times B, and then use part 3 to get A bracket times B, which is A times B. Okay, good. Question? Good. Okay. Okay, we use 5 here, and then we use 3 here. Okay, so maybe I put a job note here. Here is 5, here is 3. Okay, good. And okay, last one. 9, is it? 9. Okay, good. 9. Oh, turn out 9 not too long. Maybe shorter than 8. Any lemma? Damn. God damn. Need a lemma. Shit. Okay, I think the lemma is easy to prove. It's like linear algebra stuff. Okay, so let's do this. Well, our notation for 1 over C is like A. So this is how we define, right? So let's write it as a way that we define A times C inverse times B times D inverse. Okay. Are we allowed to commute yet? Where's my bracket? Okay, very good. Good question. So my bracket is this one. Once you go to advanced level, you know about associativity. Why associativity important is exactly because we don't want to care about bracket. You understand what I said? Because if it's not associative, you really need to care about bracket, like 1 plus 2 plus 3 equals to 1 plus 2 plus 3. So associative means this, right? Okay. If it is not associative, then you cannot just write down 1 plus 2 plus 3. If it's associative, then no matter how you bracket, it's the same. Okay. So this is the point of associativity. Okay. So make your life easier. If plus is not associative. Okay, so let's continue. So what can we do next? What's our goal? I forget our goal already. Okay, let's write down our goal. Our goal, AB over CD, Okay, so let's write down in our notation like this. Like this. Okay. So what can you observe here? I need to somehow at least move the C inverse across B first, right? Okay, and then somehow combine them into CD inverse. Okay. So what are the possibilities we can do here? Something that can swap. What's the thing that help you to swap? Start with C, commutativity. But then, now you not yet can swap anything, right? Because even if you swap, it's just C inverse with A and B and D inverse swap. So if you want to swap between B and C inverse, what do you need to do? You need to put them into the same bracket, right? But what helps you to put them into the same bracket? Associative. Okay, so you have to do a few associative first. So for example, maybe you do this first. Hey, do this is good or not? I think doesn't matter. Does it matter? No, it doesn't matter. Okay, so let's do this. Okay, and then can I associate again? Associate again? No? Okay, associate C inverse with B again. And then I make C inverse and B together now. And then I can use commutativity. Can I use or not? Because both of them are the elements in real, right? So we can use it. And then what's next? What's next? Associate again. Okay, good. So I associate back. So C inverse, D inverse. And then I associate back again. Is this the right way to associate? A, B, like this. Okay, but then something quite weird here happened, huh? I already get A, B into the right order already, but then these two guys seems different. Huh? If they are the same, you are happy. Okay, so this is next. If they are the same, you are happy. So make it the same. Make it the same. Okay, so we're gonna prove a lemma here. So lemma. If they are the same, then we are happy. So I'm gonna make it a lemma or a claim. CD inverse should be equals to C inverse D inverse. Okay, how to prove this? I think this is pretty straightforward. What's the definition of inverse? Do you remember? If you multiply from the left, multiply from the right, you should get identity. Okay, multiplicative by identity. So you just check just by checking. So C inverse, D inverse times, wait, did I get the order wrong? I get order wrong. Okay, so instead of CD inverse, okay, let me tell you the real life mathematics. Okay, let's say we write like this. Okay, I want to check. So multiply by CD, multiply by CD on the right. Is it identity or not? Where's my bracket? Very good question. Where's my bracket? So my bracket is this. I want to check whether it's an inverse of CD, right? So CD is the whole thing. Okay. So is that identity? Doesn't seem right. Doesn't seem right. So do you just throw this lemma away? We can just modify a bit, right? Can you see that? What can you do to make it identity? Swap, right? Swap means what? Commutative. Okay, so maybe we change this lemma a little bit. Okay, change this a little bit, become DC. And then here is DC. Here is DC. Then it works on, becomes 1. Okay, so meaning, okay, haven't done yet. So this one will become A dot B bracket the inverse of DC. But then DC and CD is the same thing. Make sense? Okay, so don't make a mistake and then throw away. No, adjust a little bit. Maybe it works already. Yeah. And understand? Okay, so whatever we use here is just commutativity, associativity, and then finding inverse. That's it. Okay. Yeah. So for the rest, the 10 whatever property here, you can prove similarly. Yeah. So when they prove, they put it at the first condition, right? First property here, right? Meaning this one uses the less properties. As long as you use axiom, it will jump out already. And then slowly working towards the end, you might need the previous property. Okay. Yeah. Let me see what's our next thing. Okay, so in this case here, okay, so since A times 0 is 0, right? Actually, we require these two things to be different. the identity, the additive identity and the multiplicative identity to be different. That's why we put a 0 and 1 there. Because if they are the same, then what happened, do you know? It is.
You miss one more axiom, which is 0 not equals 1. Because there's one that satisfies all of your axioms, but it's not classified as
yeah, sure. Yeah, sure. So actually, should be implied that 0 is not equal to 1 because we use different symbol, right? Otherwise, yeah, but then really, I think we need to write it out. Okay, we really need to write it out. But then, yeah, so in this case here, we require, so I make a comment here actually. Yeah, sure, we should write it in, but then I make a comment here, I can write it in later. That we actually require that 1 is not equal to 0. Okay, otherwise, I can use multiplicative identity to build this A. At the same time, it is the multiplication product with the additive identity, then we should get 0. Then what is it? There is a ring that satisfies this, which is the 0 ring. The set with 0. Just with 0, which is a kind of everything will reduce to 0. Yeah, there's something that satisfies that, but then it's obviously it's not a field. Yeah. Is it a field? Oh yeah, sure.
That 1, 0 is not equal to 1, then it is technically a field if you divide a field as.
Yeah, sure. Yes. So we require 1 is not a 0. Yeah, otherwise you will get this field, the 0 field. Empty field. Empty ring. Yeah, 0 ring. Yeah. I mean 0. New field. Okay, sure. Right. Yeah. Any questions so far? Any question? We still have 4 minutes. So maybe I briefly run through what we're gonna do next, and then we'll do it properly next class. So next we will have order axiom, meaning after we've ordered, then our real number become an ordered field. Okay, so what's order here? So meaning this order is trichotomy. Okay, as long as it's trichotomy, it's fine. But then the usual order that you learned before is a trichotomy order. So it means that any two number you take, either they are equal, either one of them is less than the other. And there's only one of this could happen. And then order preserving property, meaning your multiplication and your addition should respect your order. But then if you note the multiplication part, you have an extra condition, meaning if you multiply with a positive number only, then kind of positive, positive in this order sense. Okay.
Why don't you say non-negative?
Yeah, maybe it's another equivalent way to talk about it, but then we call this thing positive. Depend on how you define greater or equal to, but let's say we call this greater or equal to as positive, greater equal to 0 as positive. Only positive number, multiplication by positive number will preserve the order. And then reflexivity, your order have to satisfy this reflexivity, anti-symmetric, and then sensitivity. Yeah. Okay. So how we define less than or equal to is just less than or equal. We have to define what is less than, what is equal to get this order. So these are the definition. You might think this definition is how to say redundant or obvious or what, but then I wanted to say this less than sign, right? You could imagine you can swap on. Can swap. You understand what I said? The usual less than become the greater than. You can do that as long as satisfy all these properties. Okay? Yeah. So this is just really some abstract positive number, abstract negative number. So then what we can do is we can prove this. If A is in the positive side, negative, in inverse should be on the other side. Okay, this is something we can prove. And then we can prove closure of positivity under addition. So if you add two positive things, it will still stay in that positive range. And then multiplication as well. closure of positivity under multiplication, and then we will prove 1 greater than 0. Very important proof. Why is it 1 greater than 0? Okay. So far you only know 1, so far you already know 0. But for whatever order you put in, it should be 1 greater than 0. And then corollary is 1 plus 1 is non-trivial. That's why we call it 2. It's not something you know before. Corollary is 1 plus 1 is not 0. And then what else we should think about? Property of inequality. So this is the thing that you also use frequently in your calculus, right? What is that? So if you multiply with a negative number, why the inequality change sign, right? Require proof. And then why you invert your A, then you change the inequality as well, right? But now you think of this as an inverse now, right? Inverse, multiplicative inverse. Then more importantly is triangle inequality. Okay, triangle inequality is the one that we keep using later. Okay, so you have to know this triangle inequality. Okay. You know what is triangle inequality? It's almost like a Pythagoras theorem. C squared equals to A squared plus B squared. But then now you don't square them, right? So C is less than or equals to A plus B. Correct or not? Can you appreciate Pythagoras theorem or not in your real life? Strong triangle. So okay, we are not living in Peano because this is a Euclidean norm. That's not the norm we consider here. This is the usual Euclidean.
But it's but the base of the absolute value is square number.
Yeah. Okay. So so triangle inequality here just says that this side here, right? Okay, should be less than or equals to the addition of the horizontal and vertical side. If you use on the triangle, does it make sense? Do you think C is the shortest distance between that 2 points? Any path that deviates from this straight line should be longer. Do you agree or not? Do you agree? If I deviate a little bit, it's already longer already. If I deviate a bit, it's already longer. Do you agree or not? So the moral here is the shortest path between 2 points in our Euclidean space, right? In our space that we're working on is straight line. In differential geometry, we call it a geodesic. Where is the shortest path? Straight line is the shortest. If you deviate a bit, it's already a longer. If you use your ruler and measure, you should know, right? Okay, what else? And lastly is the completeness stuff. Okay, this one will be a bit more different from the rest. Okay, right. Anything to ask before I finish? No? Clear? Okay, so I'll try to give you the assignment and then you can start working on it. Yeah. Quiz. Quiz, midterm. Quiz. Little test quiz. Yes. So if the week we don't have deadline on assignment, we will have a quiz in class. Yes, we will have it next week. When is it? Can we make it a ambush one? So like anytime we will do it. What do you mean range? Oh, this week material. I will make it lecture 1 and 2. Lecture 1 and 2. And then 3 and 4, 4 and 5, 5 and 6. It's like your revision schedule. Is it okay? In that sense? Is it better? Okay. Okay, yeah. So I will test something on the logic stuff. In that sense. Yeah, we will do it anytime in the lecture times. Because you are meant to be here, right? Unless you tell me a reason why you're there. But you cannot keep running away. Right? I know some students like to run, but then 所以迟没有机会哦，所以迟 Okay, so any more question? More questions? Yeah, 所以是会给 test 对，没有错。OK 吗？还有问题吗？ No. Okay.
The test would be like on a beginning or the end because
It's actually
什么？没有，
还挺有
要提到这啊
没有不是不是
啊什么？不是，OK，没有，OK，
哪里听到？
对，我就没有看过你讲。
我是不舒服我就直接不来了。
哦，你自己不要来。
没有像如果不舒服，
哦，OK，
会不会
可以，不是你提早跟我讲了，but then
讲到
真的不舒服，
啊？
我就相信你吧。
会以后
啊什么？
80%
肯定啊，没有，OK，in this class 啊，very frank to you 啊，你不能啊，你什么啊，你就跟我讲吧，你不要骗我啦，你骗1次可以啦，可能啊，骗2次还可以啦，骗3次就啊，你自己想想看了啦，是不是？OK，所以我们玩一点人性这样啊，就是自己对自己负责任一点，
一个80%
是咩？
直接不能带。
哦，好嘞，
他想可能比他其实他什么都会很想
是可能啊，你这蔡董事没有来，
我记得那有一个公司只上过3堂课，还这么聊到
不，我看到那个 final 那个 Lisa 这个号码有一个人弄，那我觉得他应该是
哦，
可能啊，那个弄应该是有人他长期生病，反正就是你没有理由应该是电脑拿我感觉。
好嘞，没有问题，OK，还有吗？还有问题吗 ？Quiz， 没有问题，OK，then we'll see you next Wednesday， 拜三嘛，对，拜三拜四的。Then next week is a tutorial week so Friday you don't need to come for 2 hours just come for your own time Group 1 or Group 2 not Thursday, it's Friday, so we revert to Friday. Follow your original schedule. Okay. See you.